Hello students, today we are going to discuss about properties of alcohols. In the previous class we have discussed about phenols and different preparation methods of phenols, and also we have discussed the acidity of phenols and also some reactions, the electrophilic substitution reactions of phenols. In this class we are going to discuss about some named reactions of phenols. Before going to the named reactions of phenols, let us revise the electrophilic substitution reactions of phenols also. See, phenol in which the OH group is directly attached to the carbon of aromatic ring. See here, coming to the reactions of phenols, we know that phenols are having acidic nature. These phenols are strong acids than alcohols, and they are having weak acidic nature than carboxylic acids. And the reactions that show the acidity of phenol is this is the reaction. That means phenol, when reacts with sodium hydroxide, that is a strong base. Phenol reacts with sodium hydroxide, it gives sodium phenoxide, while in case of this with reaction with sodium bicarbonate, there is no reaction. And we know that phenols are having weak acidic nature, and they are weak acids than carbonic acid, hence they are soluble only in sodium hydroxide, that is strong base. That is, phenols are soluble in 5% NaOH solution, while phenols are insoluble in 5% NaHCO3. That means these reactions they show the acidity of phenols. And coming to the reactions of phenol, already we have studied that phenols they readily undergo electrophilic substitution reactions. Coming to benzene, we know that benzene undergoes electrophilic substitution reactions. They do not undergo addition reactions, they undergo only substitution reactions. In that substitution reactions, again they undergo only electrophilic substitution reactions, because as they are having more electron density, they undergo electrophilic substitution reactions. While coming to phenol, we know that see here, if you observe the resonance structures of phenol, these are the resonance structures of phenol. In these, see, if we observe the resonance structures, there is negative charge arises at ortho and para positions. Negative charge arises at ortho and para positions. See here, negative charge arises at ortho and para positions. That means there is more electron density available at ortho and para positions. Hence, phenol readily undergoes electrophilic substitution reactions than benzene, because in phenols the OH group it facilitates the electrophilic substitution reactions, as it is, that is the OH group, the electron pairs on OH group or in conjugation with the aromatic ring. Hence it increases the electron density. So phenols they readily undergo electrophilic substitution reactions. And coming to See here, phenols are very reactive towards electrophilic substitution reactions. The OH group is strongly activating ortho-para directing group. And see here, the general electrophilic substitution reactions are like this. When phenol reacts with, it means the electrophile, it attacks at ortho and para positions because the OH group is ortho-para directing group. The coming electrophile, it attacks at ortho position or para positions. Hence, two types of products are possible, that is ortho product and para product. Two types of products are possible, ortho product and para product. This is about electrophilic substitution reactions of phenols. Let us see some examples for electrophilic substitution reactions. In that, in the syllabus we have nitration, sulfonation, halogenation, alkylation and acylation also. See here, coming to nitration, see here in nitration reactions the electrophile is in nitronium ion, that is, and this electrophilic substitution reaction, the products are depending upon the concentration of the nitric acid. If phenol reacts with a dilute HNO3 or dilute nitric acid, orthonitrophenol and paranitrophenol are the products formed in the reaction. That is, with the reaction with dilute HNO3, orthonitrophenol and paranitроphenols are formed. While coming to when phenol is treated with concentrated nitric acid, trinitrophenol is formed. That is 2,4,6 trinitrophenol is the product. The reaction is vigorous and it forms this 2,4,6 trinitrophenol is formed. This is about nitration reaction with dilute nitric acid. Orthonitrophenol and paranitроphenols are formed, but with concentrated nitric acid, trinitrophenol is formed. And next, halogenation. This halogenation, it also depends upon the type of solvent used in the reaction. For example, if phenol reacts with bromine in non-polar solvents like carbon disulfide or dichloromethane, orthobromophenol and parabromophenols are formed. That means when phenol is treated with bromine in non-polar solvents like carbon disulfide, orthobromophenol and parabromophenols are formed as products. While if bromination or halogenation takes place in polar solvents like water, see here, if phenol is treated with bromine in water, the reaction is vigorous and it forms a tribromophenol, that is 2,4,6 tribromophenol is formed as the product. See here, halogenation in halogenation or this in bromination, the solvent plays important role. The reaction of bromine in non-polar solvent with phenol, it gives orthobromophenol and parabromophenol as products. While in case the phenol reacts with bromine in aqueous solution, that is polar solvent, it forms a tribromophenol as product. And here, this is sulfonation reaction. The sulfonation reactions, it depends upon the temperature. When phenol is treated with concentrated H2SO4 at low temperature and high temperature. At low temperature, that is around 20 degrees centigrade, the ortho product is formed. At 100 degrees centigrade, para product is formed. At 20 degrees centigrade, orthohydroxybenzene sulfonic acid is the product. At 100 degrees centigrade, para-hydroxybenzene sulfonic acid is the product. That means depending upon the temperature, the product is changed. And here, the next reaction is alkylation reaction. That is Friedel-Crafts alkylation. That means when phenol is treated with alkyl halide in the presence of anhydrous AlCl3, it forms alkylated product. Here crystals are formed, that is paracrystal and orthocrystal are the products formed in this reaction. When that means when phenol is treated with methyl chloride in the presence of anhydrous AlCl3, we get this mixture of crystals, ortho and paracrystals. And next, see here, next acylation reaction. When phenol is treated with acid chlorides in the presence of anhydrous AlCl3, that is when see here this reaction when phenol is treated with acetyl chloride in the presence of anhydrous AlCl3. See here again here in this reaction there may be possible first two types of acylations are possible. One is, see here, I will write here just a minute. This is benzene. See here at oxygen also the acylation is possible. At oxygen also acylation is possible, but it again rearranges to these products, this and this. That means actually this acylation takes place on oxygen as well as carbon. If O acylation takes place, it again undergoes rearrangement to form these products. But the final products are these. That is when phenol is treated with acetyl chloride in presence of anhydrous AlCl3, this ortho product and para products are formed. And next, see here, reaction with alkyl halides. See here when phenol reacts with alkyl halide in the presence of base, they form ethers. See here with in the presence of base like sodium hydroxide, already we know that phenols are having acidic character, and in the presence of base they form phenoxide ion, and they form phenoxide ion. That is phenol with base, they form phenoxide ion, and treating with alkyl halides it forms ether. It forms ether. And see here this reaction when phenol is treated with ethyl iodide, that is alkyl halide ethyl iodide in the presence of base, it forms this phenyl ethyl ether as the product. That means ethers are the product in the reaction of phenols with alkyl halides. And next, see here, coming to some named reactions we are going to discuss in this class. First one is Riemann-Tiemann reaction. In this the phenol is converted into orthohydroxy benzaldehyde using chloroform. That is phenol is treated with chloroform in the presence of base, it forms orthohydroxy benzaldehyde, that is commonly known as salicylaldehyde. It means formylation takes place at ortho position in this reaction. Riemann-Tiemann formylation takes place. The reaction is when phenol is treated with chloroform in the presence of base, it forms, that is O formylation takes place at the ortho position, that is orthohydroxy benzaldehyde is formed. And the common name of the compound is salicylaldehyde. Phenol treating with chloroform in the presence of base, it forms salicylaldehyde. See here this is the reaction mechanism also very important in this reaction. See here first of all, in basic condition when it is treated that means in the presence of base, this chloroform loses one proton and it forms this carbon ion CCl3 minus, and with the loss of one more chloride ion it forms a dichlorocarbene. And in the next step, see here, we know that in the presence of base it forms phenoxide and the phenol it converted into phenoxide ion with the loss of proton. And to this phenoxide ion, see here this is dichlorocarbene. and here this shifting of minus charge to this, and this bond attacks here at this carbon. This attacks at this carbon, and here if you see the bond is formed between carbon of aromatic ring and carbon of this dichlorocarbon, and here we get double bond, and here we get single bond. That means double bond is converted into single bond. And in the next step, see here, this hydrogen goes to this carbon, this hydrogen goes to this carbon, and we get CHCl2 here, and this rearrangement takes place like this. We get double bond here, and we get single bond here, and we get minus charge here. And in the next step, see here, this CHCl2 group is there. In the presence of base, see here, first one chlorine is substituted with OH group, and with the elimination of C here, some rearrangement takes place. This chlorine is removed as Cl minus, and this proton is also removed, and we get here CHO group, and just followed by with that means the proton is added to oxygen, and we get orthohydroxy salicylaldehyde. See here, the mechanism is very important. In the first step, the dichloroform, in the presence of base, it is converted into dichlorocarbon, and in the second step, the phenoxide ion, this dichlorocarbon attacks at ortho position, and the rearrangement of hydrogen to this carbon ion, we get CHCl2 at ortho position, and the CHCl2 in the presence of OH minus, one chlorine is substituted with hydrogen, and followed by some rearrangements, we get aldehyde group at ortho position, and by adding H plus at oxygen, we get this salicylaldehyde as a product. Hope you understood this reaction. This is about Riemann-Tiemann reaction, that is formulation of phenol at ortho position in the presence of base. When phenol reacted with chloroform in the presence of base, formulation takes place at ortho position. And next, coming to this Kolbe reaction. See here, when phenol is treated with sodium hydroxide, we know that sodium phenoxide is produced. That means in the presence of base, when phenol is treated with carbon dioxide followed by acidification, it undergoes electrophilic substitution to give a hydroxybenzoic acid as the main product. That means same like Riemann-Tiemann, in the presence of base, if phenol is treated with carbon dioxide, it gives hydroxybenzoic acid as the product. See here, this is the reaction in which phenol, first of all, in the presence of base, it forms that means base and CO2, it forms this orthohydroxybenzoic acid, that is salicylic acid. While in case of Riemann-Tiemann reaction, same, in the place of the COOH, CHO group is added, that is formed. Here at ortho position, COH group, that is orthohydroxybenzoic acid or salicylic acid, is formed as a product. That is, when phenol is treated with carbon dioxide in the presence of basic conditions, it forms orthohydroxybenzoic acid is as the main product. Meanwhile, that means actually sodium salicylate is formed, which upon it converted into salicylic acid. This is the Kolbe reaction with carbon dioxide in the presence of basic condition to give salicylic acid as the product. And see here, coming to the mechanism, Again, this is the reaction, phenol with carbon dioxide in the presence of basic condition. It gives salicylic acid. First of all, this is phenol in the presence of basic condition. It forms phenoxide ion, and with this CO2, see here, some rearrangement takes place like this, and this bond attacks with this carbon, and we get, see here, double bond here at that means oxygen, it becomes double bond here, and we get bond here. This carbon is attached to the aromatic ring, and we get here O minus. And in the next step, see here, some rearrangement here. This keto group is converted into enol, like this, en and ol, and we get this molecule. Okay, this is the mechanism. See here, first phenol in the presence of base, it forms phenoxide ion, which that means this phenoxide ion, it again this bond formation, that is at ortho position. See here, this minus charge comes here, and this double bond attacks at this carbon. So I mean this rearrangement takes place, and we get double bond here, and we get a new bond formed between this aromatic ring and the carbon of the carbon dioxide. And next, see here, this keto group is converted into enol, and we get CO2 minus with H plus. Here we get salicylic acid is as the product. This is about Kolbe's reaction. In Kolbe's reaction, when phenol is treated with carbon dioxide in the presence of basic conditions like sodium hydroxide, it forms salicylic acid. Coming to this Houben-hoesch reaction, see here, this nitrile here reacts with not this trinitrophenol but arene compounds, trihydroxybenzene generally. Nitrile reacts with arene in the presence of Lewis acid and HCl. It gives aryl ketone. Here in this compound, aryl ketones are the products. That means when the cyanides, they react with arenes in the presence of Lewis acid like ZnCl2 and HCl, they give aryl ketone. And here this is trihydroxyphenol. When it is treated with this methyl cyanide in the presence of Lewis acid like ZnCl2 and HCl, and these are the conditions, that is 5 to 10 degrees centigrade, and around 24 hours the reaction should be carried out in the presence of that means solvent is diethyl ether, and it forms, see here, this ketone, that means aryl ketones are the products formed in this. First of all, this between the intermediate is ketimine intermediate, which followed by hydrolysis, it gives aryl ketones, that is trihydroxyphenol when it is treated with methyl cyanide in the presence of ZnCl2 and HCl at 5 to 10 degrees centigrade. It forms first ketimine, which upon hydrolysis it forms ketone, that is aryl ketones are the products formed. See here, this is the mechanism of Houben-hoesch reaction, in which aryl ketones are the products. The trihydroxyphenol reacts with methyl cyanide in the presence of ZnCl2 and HCl. See, first of all, ZnCl2, we know that it is a Lewis acid, and see here, this cyanide we have OH group here in this phenol due to this like this. See here mechanism, this electron pair here, this double bond like this, and here this shifts here, and we get bond here between the carbon of the cyanide and to the aromatic ring, and we get here this is formed, that is a ketimine, is formed here. See here ketimine is formed, and next see here this hydrogen, again the rearrangement. See here we get OH here, and we get this ketimine, and followed by hydrolysis. See here this oxygen attacks here, and it becomes, see here NH2 here like this, and with the removal of this H and NH2, NH3 is removed, and we get aryl ketone here. So very simple mechanism. First of all, this is trihydrophenol, and this shifting like this. See here, and here in this way the bond is formed between the carbon and aromatic ring, and here next the rearrangement for the formation of again this OH, and next attack of this water molecule, and with HCl we get here OH, and this become NH2, and next the rearrangement, this, see here this oxygen, the single bond become double bond, and this NH2 and this H as NH3 removed, and we get this aryl ketone. This is about Houben-Hoesch reaction. In this reaction, this trihydroxyphenol, it reacts with this methyl cyanide, and in the presence of ZnCl2 and HCl, it forms aryl ketones. This is the reaction. And see here the next one more reaction is Schotten-Baumann reaction. This is about Schotten-Baumann reaction. This is Schotten-Baumann reaction. In this in this Schotten-Baumann reaction, these phenols, they are treated, they react with Acylhalides or esters, and they form, esters are the products in this Schotten-Baumann reaction when phenols are reacted with Acylhalides or anhydrides. Here esters are the product, in which first of all the oxygen of the phenol, it attacks at the carbonyl carbon of the this Acylhalides, and then it rearranges to eliminate the halide. Then afterwards the deprotonation takes place in the presence of base, and it forms ester. See here, actually this is the reaction here. Here this is the reaction. In this here phenols are taken, alcohols are as well as phenols also taken. See here, if this is phenol, it reacts with acid halide, acyl halide under generally basic conditions, it forms this ester. See here, this is the mechanism of this Schotten-Baumann reaction. Here first of all the oxygen of the phenol, it attacks at this carbonyl carbon and shifting of this double bond to oxygen, and we get negative charge here, and we get single bond here, and we get positive charge here. Next of all rearrangement takes place to eliminate the halogen as halide, and see here the minus charge here, and this X is removed as X minus. We get double bond here, and see here, and next the deprotonation takes place in the presence of base, it forms ester. This is the mechanism, and very simple mechanism, not so complicated. First of all, attacking of this oxygen of the phenol on this carbonyl carbon, and we get, see here, this becomes single bond here, we get minus charge here, and we get plus charge on oxygen. And next, see here, this rearrangement, this minus charge again to here, and this X is eliminated as X minus. That is, in the second step, the halogen is removed as halide ion. And next, in the third step, see here, this deproduction takes place of this hydrogen in the presence of this OH minus. It gives ester. Ester is the final product here, ester. And next, see here, that is, this is the Schotten-Baumann reaction, in which this phenols, they react with Acylhalides or anhydrates, and they form esters. This is about a Schotten-Baumann reaction. And next is Azo-coupling reaction. In this, phenol reacts with benzene diazonium chloride to give a yellow-orange azo compound. The reaction is carried out in basic conditions. See here, in the presence of base, this phenol reacts with benzene diazonium chloride to give a yellow-orange azo compound. This is known as azo-coupling reaction. That is, this phenol, it is reacted with benzene diazonium chloride, and here some rearrangement takes place to form this azo compound. See here, here directly mechanism given. See here, this OH facilitates the attacking, that means the bond formation between this nitrogen and this carbon. See here, this rearrangement is like this electron pair like this, next rearrangement like this, and bond forms here. Here, this thick bond, the bond formed between nitrogen and carbon, this para carbon. And next, see here, this hydrogen is eliminated. Again, see here, this hydrogen is eliminated, and we get I's to the formation of azo compound. See here, in the step, this hydrogen is eliminated as HCl, and we get rearrangement like this, and we get the yellow-orange azo compound. This is the azo-coupling reaction, that is phenol, it reacts with benzene diazonium chloride in the presence of basic conditions. It forms yellow-orange azo compound. This is known as azo-coupling reaction. And here, this benzene diazonium chloride is obtained by, that is from aniline. When aniline is treated with sodium nitrite and HCl at low temperatures around 0 degrees centigrade, 0 to 5 degrees centigrade, it gives benzene diazonium chloride. That is, actually, in this azo-coupling reaction, the phenol reacts with benzene diazonium chloride. This benzene diazonium chloride, we get this benzene diazonium chloride by treating this aniline with sodium nitrite and HCl at 0 degrees centigrade. Generally, it gives this benzene diazonium chloride, and with this benzene diazonium chloride, it reacts with phenol in the presence of base, and it forms azo compound. This is azo-coupling reaction. Next, reaction with FeCl3. It is actually a reaction to, it distinguishes the phenols from alcohols. It distinguishes with the that means it differentiates the phenol from alcohols. And these phenols, they react with ferric chloride, they form a purple complex. And the phenoxide ions, they form coordinate bonds with the Fe+3 ion, while the hydrogen from phenol stays in ionic form to form with chloride ion. See here, this phenol, it forms a complex molecule with this FeCl3. This reaction with FeCl3, it is used to distinguish the phenols from alcohols. See here, this is phenol with this ferric chloride. It forms this type of complex. See here, iron phenol complex is formed here. This is actually violet in color. That is, when phenol is treated with this ferric chloride, it forms a complex, violet color complex. That is iron phenol complex, and this reaction is used to distinguish the phenols and alcohols. In case of phenols, this violet color complex is formed so that we can differentiate phenols and alcohols. And these are the reaction with this, actually these are the name reactions of phenol. And today we have discussed the name reaction, that is Riemann-Tiemann reaction. And next, Schotten-Baumann reaction, Kolbe reaction, Houben-hoesch reaction, Azo-coupling reaction, and the reaction with FeCl3. That is, in Riemann-Tiemann reaction, when phenol, it is treated with chloroform in the presence of basic conditions, it forms, that is, formylation takes place at ortho position. That is, orthohydroxybenzoaldehyde is formed, that is known as salicylaldehyde is formed in this reaction. And next, coming to Kolbe's reaction, in this, this phenol is treated with carbon dioxide in the presence of basic conditions. It forms salicylic acid. That means salicylic acid is formed in this Kolbe's reaction when phenol is treated with carbon dioxide in the presence of basic condition. This is Kolbe's reaction. Next, Houben-hoesch reaction, when nitrile reacts with this trihydroxybenzene in the presence of this, when this trihydroxybenzene is reacted with methyl cyanide in the presence of zinc chloride, that is Lewis acid, and with HCl, they forms first ketimines. This ketimines, upon hydrolysis, it forms aryl ketones. That means in this Houben-hoesch reaction, aryl ketones are the main products. And here, this is the mechanism. Okay, we have gone through it. And next is Schotten-Baumann reaction, in which the phenol reacts with acylhalides or anhydrides to form ester. Already we have studied this. When phenol is treated with acylhalide and anhydride, and it forms ester. This is the mechanism we have studied just now. And next, Azo-coupling reaction, when phenol is it is reacted with benzene diazonium chloride, it forms an yellow orange azo compound. This is known as Azo-coupling reaction. And the benzene diazonium chloride, we get the benzene diazonium chloride by treating this aniline with sodium nitrate and sodium nitrite and HCl in the at 0 degree centigrade. It produces benzene diazonium chloride, and this benzene diazonium chloride with phenol, it forms azo compound, yellow orange color azo compound. And next, the last one is the reaction with FeCl3. This is the reaction used to distinguish phenols from alcohols. When phenols they react with this ferric chloride, it forms a purple complex in which the phenoxide ions they form coordinates bonds with Fe+3. This phenol forms iron phenol complex which is violet in color. By using this reaction we can differentiate phenols. Phenols form this color complex while alcohols not. With this I conclude today's session. With this the phenol chapter is over, and in the next class we will go with another chapter. That means in this chapter we have discussed about alcohols and phenols, that is introduction to alcohols, classification of alcohols, nomenclature of alcohols, synthesis of alcohols, of course the acidity of alcohols, properties of alcohols also discussed in the previous classes. And coming to phenols, in the phenols also we have discussed about introduction to phenols and synthesis of phenols. Of course the important, that is acidity of phenols, that is phenols are stronger acids than alcohols but weaker than carboxylic acids, and various synthetic methods for the preparation of phenols and the properties of phenols, that is chemical reactions of phenols. In that name reactions we have discussed today. With this the chapter is over. With this I conclude this today's class. Thank you.